delight to introduce the next speaker, who is Dr. Nicolas Michel, a postdoc here at the University of Cambridge and also affiliated to the Open University, who will be speaking to us on ways of curve making, ideals and practices of objectivity in the theory of algebraic curves. Thank you, Nicolas.
Thank you, Bridget, and thanks, Chris, for having me and inviting me here to look ahead, however myopic I might be. I'll begin by quoting from one of several papers which Catherine Goldstein devoted to the figure of Charles Hermite, so quite far from geometry. Papers in which she tries to describe Charles Hermite's work, especially on quadratic forms and related topics, as the work of a naturalist. And I will not get into any of the mathematical details, but essentially she argues that what we observe in Hermite's practice in his theory is that it's a practice that is sort of like that of a naturalist, in which the foundation of a theory, of a mathematical theory, is not to be found in new concepts, in the selection of axioms, in formalization, but rather in the identification of specific results, formulas that can reproduce the organizing principle from which the main theorems of a theory can be deduced. That is to say, the mathematician is not in the business of inventing a new concept, just as a naturalist is not in the business of inventing new organs or organisms, but rather their task is to detect new organisms within known species, or revealing how we can identify characteristic traits, properties that allow for classification of existing organisms or mathematical objects, highlighting what the right characteristic features, the right types, the right classificatory principles are conducive to good classifications, to good descriptions of a world of natural objects, whether they be organisms or quadratic forms. And this is a particularly interesting description for me, because I observe similar phenomena in the history of geometry, and especially in the context of algebraic curves, with specific problems relating to geometry than algebra. And what this description suggests to me, or what it invites me to pursue, are two broader questions that I think can be of interest to historians of mathematics, especially modern mathematics, beyond the actors and the terrains that I'm interested in. The first question is, what sort of cognitive labor goes into mathematical research? So immediate answers come in the shape of terms that we are very familiar with, so theorem proving, computations, axiomatization, and so on. But what these papers suggest is that we can also answer with descriptors that borrow from other epistemic activities or other sciences in the way that she describes Hermite's work on algebra. A great deal of attention must be paid to practices such as observation, classification, comparison, ordering, non-deductive practices that resemble those that we find other kinds of scientists routinely employing and thinking about. And so this also suggests using categories to describe specific mathematical texts or practices that are not field-specific, theory-specific, object-specific, and so on, that cut across a much broader spectrum of activities, whether within mathematics or beyond. And so a first question also related to this is what new images, chronologies, categorizations emerge when we look at the history of geometry with concepts of this nature that are not specific to mathematics or that are not specific to geometry. And the second related question that this inspires me is the question of how mathematicians relate with the object of their research at the level of their daily practice. We'll be saying very little about how mathematicians reflect about objects or objectivity, especially, so I'm focusing on the period, the second half of the 19th century, that is rife with mathematicians' reflections on what mathematical objects are, whether there is such a thing as objectivity in mathematics, and so on. But I will leave that aside almost entirely, and instead try to describe, just like Catherine Goldstein does, the concrete ways, the concrete practices through which mathematicians relate with objects of scientific inquiry. And this is related to the first question, because just as scientists are always in the business of constructing objects of collective inquiry and of selecting things that they can talk about together and represent in a way that can circulate, then so do mathematicians need to construct these objects, whether it be through the creation of certain symbolisms, notations, other kinds of verbal or diagrammatic tools. And sometimes we find that those practices do not fully match what their discourse on their object is. And so, yeah. And so I want to describe how several actors, in my case, in the theory of algebraic curves, come up with ways to carry out, to practice this objectivity. And I will try to suggest that we can map out several practices of objectivity, and that this provides new and interesting perspectives on not only the history of geometry, but the history of mathematics at this crucial junction writ large. So what I will try to do today is contrast two actors who, both of whom share, broadly speaking, a realistic commitment towards mathematical objects, who, broadly speaking, think that their research deals with things that exist in some shape or form, that share worries about the lack of rigor and precision in modern geometry. It's something that needs to be remedied, but who use very different strategies and ways of engaging with mathematical objects to do just that. And also two mathematicians who share many research objects, research questions, but who answer them in very different ways. And hopefully they will build towards a convincing picture of why this is an interesting perspective on the history of modern mathematics. So the first of these two mathematicians is the French geometer and mathematician Georges-Henri Elphen, who was born in 1844 in Rouen, and who died quite young, as you can see, at the age of 45. He would go on to interact with Hermite quite a lot, although he didn't study at the Hermite because he went to the École Polytechnique and then had a career as a military man, as a lieutenant d'artillerie. But someone who maintained a steady stream of publications and scientific activities all through his life, despite being very busy with his military duties. He wrote on a selection of topics, quite an exhaustive array of subjects. I will only focus on a few. So his first publications in the late 60s deal with congruences of lines, skew curves. Skew curves being a topic he would return later on in the 80s, in light of work that he had been done in the meantime. He also wrote important papers on algebraic curves and their singularities, on systems of conics and quadrics. He was a répétiteur at the École Polytechnique. He eventually gained membership at the Académie des Sciences. So he's someone who was quite successful as well institutionally, someone who was widely recognized by his peers as an important mathematician. When he died, his collected works were edited by people like Poincaré, Hermite, Picard, someone who was very much known by all and well appreciated in leading institutions. So very much someone who, even though he was working as a military man, he was very much recognized by all professional mathematicians of his days, and very much lauded for his analytical skills, his rigor, the perfection of his memoirs, and so on. And so what I want to do is I will give a very superficial description of two of his memoirs, in order to build an image of how he engages with mathematical objects and how he understands what he understands the main task of mathematical research to be. So the first one, and to do that, I will start with a letter that he wrote to his good friend, the Danish geometer Hieronymus Zeuthen, in 1879, in the course of a dispute with another German mathematician. I will get into that. And At this point, he's several letters into the dispute. He's quite annoyed, and he writes to his friend Zeuthen, there is no general system of conics of characteristic mu, just like there is no general skew curve of degree m. One cannot reason on what does not exist. Here's how we may nonetheless obtain theorems, such as the one that you call general. And then he goes on. He says, so he tries to say, the issue with my opponents in this debate is that they try to reason, they try to discuss on objects that simply do not exist, on fictitious beings that cannot be properly defined. And why can't they be properly defined? Because they depend on several equations. Of all the argument that one may levy against supposedly general theorems, so theorems that bear on these fictitious beings, the problem is the following. Whatever justification one may offer disappears when these beings, les êtres, are defined by more than one equation. And because these objects are ill-defined, there's a sort of a leeway. We can choose to represent them by one equation or the other, and this leads the theorems to crumble. They have no solidity to them. We must give up on intuition and return to analysis. So a well-known trope at the time that geometry, unlike arithmetic or algebra, has not undergone the process of rigorization that is necessary. And so worried that Halphen viewed himself as having to quell. So what is interesting to me here is that he begins with two examples. So systems of conics, so this is one family of conics in the plane, or the algebraic skew curve in three-dimensional plane space, which he describes as non-beings. And this really evokes, and this is where the comparison with naturalism is interesting. This echoes, or this resembles the very famous claim by Stephen Jay Gould in his well-known paper that there is no such thing as a fish. That is to say that, sure, there are many kinds of vertebrates that we can identify that live in water, but from the viewpoint of genomics, they do not form a coherent group, what he calls a cladistic group. And the problem, he continues, arises from the complexity of the world, not from the fuzziness of our thought. Morphology alone, or similarity between organisms, is no proper basis upon which to create objects. Because if we create our objects purely on those resemblances, on these morphological similarities, we come up with objects that crumble under serious scientific inquiry. And this is not something to be lamented, but rather something to be rejoiced by. I do not believe that nature frustrates us by design, but I rejoice in her intransigence nonetheless. And in effect, Halphen was carrying out a similar move, saying, if we want to look at complex geometrical objects, such as systems of conics or skew curves in space, we cannot use simplistic classification schemes, such as what he calls a characteristic in the first case, or the degree in the second, because these numbers, these characteristics do not provide us with the right classification scheme. They do not provide us with the right tools to understand the complexity of natural order. So what does this mean concretely? So in the first case, systems of conics. So here's what Halphen is trying to tell us. So this is one of his first major scientific contributions over the course of the 1870s. So here he's building on works by Michel Charles, Zeuthen himself, de Jonquière, Cremona, and many others from the previous decade. And so he's tackling a question on which there's an extensive body of literature, the main question of which is how many conics in a given system, so an algebraic one family of conics in the plane, satisfy a given condition. So for instance, touch a given curve, pass through a given point, and so on. And so there was a theorem, or rather a conjecture, laid out by Michel Charles some 10 years in the 60s, that said that there is a way, and I will not get into it, but there is a way to attach two numbers to systems of conics and similarly to attach two numbers to conditions, such that those objects are fully accounted for by these two numbers. You may look at them as the equivalent of the order and the class of a plane algebraic curve. So if, for instance, in the theory of plane algebraic curves, knowing the order, in a way, gives you all the answers you may want to with regard to enumerative questions. For instance, how many intersections do two algebraic curves have? Well, the product of their degrees. So here they thought, well, it's slightly more complicated. We need not only one, but two numbers. So let's say the order and the class of the curve. And then there's a Bezout-like theorem. Instead of having just a product, we have the sum of two products. But essentially, those two pairs of numbers characterize these objects and give us general answers. And Halphen's main contribution in this series of papers was to prove that, in fact, those two numbers do not fully characterize a given system. This is a faulty classification that the system of characteristic mu is a non-object, something that simply cannot be made into a solid conceptual basis for the study of systems of curves. And so how did he go about proving that or refuting that, rather? Well, his strategy, which we will see comes up in other of his many others of his publications, is to attach to this complicated object, which is the system of curve, a simpler object, namely a plain algebraic curve. So he says in this memoir from 1878, but really the conclusion of many other earlier works, everything useful, all the useful elements that relate to a system of conics can be represented by a curve that we might call attached to the system, or sometimes he calls it an indicatrice, an indicatrice. So there's this strategy which consists in attaching point by point, pointwise, the conics in the system to the point of an algebraic curve, such that all the properties of the system can be obtained by looking at what happens at the level of the curve. So here's one way of there are many ways to construct such curves, to attach curves to a system, which have various properties and which are more or less convenient. But here's one, which is not the one that he will settle on, but one that is sufficiently easy to understand to give us an idea of the method. So here's what he does in this case. He says, well, so I have my system of conics. So I have conics which you can think of it as you take the general equation of a conic and the coefficients are algebraic functions of a parameter. To simplify it, he says, well, we can for every value of this parameter we can find a triangle such that the equation of the conic with respect to this triangle in homogeneous coordinates has this simple form, this sort of a diagonal matrix, this allows us to represent to have three coefficients which correspond to the conics of the system, and these three coefficients in turn can be viewed as the homogeneous coordinate of a point in the plane, and so each conic of the system is mapped out to a point in the plane, or that is to say, the system is mapped to an algebraic curve. The details don't really matter. But so we have this procedure through which we associate conics in the system to points of an algebraic curve. And one important property of this way of associating a system to a curve is that the conics in the system are degenerate only when so for this conic to be degenerate, one of the GIs has to be 0. That is to say, we have our triangular system of coordinates. So the conics of the system which are degenerate correspond to points of the curve which intersect one of the three sides of the triangle. And so we can geometrically describe looking at when the curve intersects the triangle, we can describe when the moments at which the conics in the system are degenerate. And what's more, looking at the multiplicity with which the curve intersects the triangle, we can sort of we can say the multiplicity of those degenerate conics and how conics degenerate in the system, at which rate, and so on. And this allows a transfer of the study of singularities and multiplicities in the case of algebraic plane curves, which is a well-known theory at the time that Alfvén is fully in possession of, to study this more complicated object, which is the system of conics, where it's much more difficult to speak with precision of the degeneration in this object. And it turns out, Alfvén shows through this carryover of the theory of singularity towards this more complicated object, that we can obtain a classification of the degenerate conics in the system by distinguishing between several cases: when only one coefficient becomes 0, when two coefficients become 0 at the same rate, or when two coefficients become 0 at different rates. And he goes on to explain to us that when two coefficients become 0 at different rates, then the ratio of the rates at which they vanish, which he writes 1 plus h, that is the falsifying principle to the classification, because in fact this yields an infinite series of possible degenerate conics. Right? For each ratio, there is a new kind of degenerate conics that appear. Namely, the first kind can be interpreted as conics that degenerate into two straight lines with one double point. The second kind corresponds to conics which degenerate as one. For instance, you can think of an ellipse. You pinch the two endpoints, and the ellipse flattens. So you have one line with two specific points here. And the third kind, which is depicted here, becomes one straight line with one point playing a specific role. So it's here the third kind. And the ratio at which the semi-axis degenerate, that is your 1 plus h. So here you have a hyperbola. Both diameters vanish to 0, but they vanish at different rates. And so the ratio of the rates at which those diameters vanish, this is this 1 plus h. And for each different value of 1 plus h, the conic behaves differently with regards to enumerative questions. And so what Alfvén concludes from a very complicated analytical study, which I do not get into, is that rather than having a formula like alpha mu plus beta nu, in fact, you must add additional terms, and for each ratio 1 plus h that occurs in the system, you must add a new term. So in other words, there is no finite formula to be hoped for. All there is a procedure. You determine what ratios 1 plus h appear in your system, and you add the corresponding number of terms. So what it gives you is not a formula, but a method for the extension of the formula. And this is based on the fact that algebraic analysis reveals to you that what you thought was a general object does not in fact exist. That nature is more quirky, more intelligent than what you thought. And what's interesting is that this is exactly the same strategic move, the same mode of investigation that he would carry out in his famous memoir on skew curves. So this is a memoir published in 1882, which was awarded the Steiner Prize, but which corresponds in part to an earlier memoir he had written in 1869 for the Academy in Paris, but which had not been published. The starting point of this memoir, just like in the case of systems conic, is to say, well, in the plane, the degree of a curve yields a sufficient classification, right? We can just say, well, algebraic plane curves can be split into classes that are defined by this one number. In space, this does not work because as soon as we can define the degree of of a skew curve, but this is not a sufficient principle to classify curves, because as soon as this degree is higher than 3, then we can come up with questions with properties that requires further specification. Here's an example that he gives. So in the case d equals 3, there's only one family of curves, the skew cubic, but for d equals 4, we have two cases, one in which the curve is the intersection of two quadrics, and one in which is the intersection of a quadric of two surfaces of degree 2 and 3 plus some additional straight lines. So it must be complemented. And he goes on to say, well, sometimes we used to think that we could remedy this situation by adding a second number to the degree. We could consider the number of apparent double points. So we're looking here at smooth skew curves, but even a smooth skew curve when projected onto a plane may appear to have double points. So there was this idea that by considering this additional number, this additional characteristic property, let's say, then we might solve the problem. And so if you look here, for instance, in the case of degree d and 4, d equals 4 or d equals 5, we can have a full classification just by distinguishing between certain values for this number h, which is the number of apparent double points. So for instance, in the case of degree 5, well, there's only 3 possibilities. They can be 0, 3, or 4 double points. And then that yields a full classification. But, he explains, for curves of degree 6, that doesn't work anymore. And he goes on, he says, well, then let's add the genus. And the genus, so with a third number like the genus, then you can have a full classification of curves of the 6th degree. But from the degree 9, even the genus is not enough. And so his point being, well, there's no hope that any sort of finite amount of tweaking will work. There will always, at some point, you will always need to add something more. And so he gives examples. This is very complicated geometry. I have no hope of explaining what little I understand of it to you in this amount of time. But essentially, but we can look at it later on. And so how does he go? But the point is not to just have this negative answer to say, well, there's no hope of classification. His strategy instead is to say, well, let's consider various analytic representations of those skew curves, and let's use them to figure out in which cases we can still provide classifications, albeit partial ones. And so he goes on to say, well, one way of looking at skew curves that is particularly fruitful is to look at them as intersections of surfaces, but that has issues. Another one is to look at them as being defined by those auxiliary polynomials. So the first equation is the projection of the skew curve into an arbitrary plane, and then you have those two other polynomials, phi and xi, and you can have this. So this equation sort of represents the skew curve. So you have one parameter z, which essentially you can look at it as like you have a mobile plane, and each time you're looking at one algebraic expression for the projection of the curve on that plane. So z, x, y, and z sort of are, in a way, coordinates of the points of the curve, albeit related by these very artificial polynomials, which don't really have, which, as he explains, do not have a geometrical definition. They are purely artificial means of representation, for which there's a great amount of leeway. But the point being that if you're a skillful wielder of this analytical apparatus, you can use those polynomials to map out cases in which a classification is possible. And for instance, he goes on to explain. Sorry, yeah. so here, when the degree n of xi, so xi is the denominator here, so he's able to show that when this polynomial xi is of sufficiently low degree, then we can still provide a full classification of the curves of a certain degree and with a certain number of apparent double points. And not only that, but in fact he's able to provide a rational method for the continuation of the classification when this degree is within certain bounds. So here's what so this is a very long memoir, about 200 pages, and this is what about half of it looks like. You have those tables. So here, for instance, courbe du 5e degré. So this is the first case in which, for curve of the 5th degree, when this number n is equal to 2, which is the only possibility for which it's low enough, then you have a full classification, which is able to spell out here. And then he goes on to explain that to give here a procedure for the he gives the tables for 6, 7, 8, 9 as well, and then he stops at 9 and he says, well, then here's the procedure through which you can continue the operation, because I mean it's an infinite process, right? There's always more to be computed, but he gives the procedure, the modification that you need to carry out, and the process. He gives some more examples, and he gives two methods, and he says it's easy for the reader to check through the same methods all the numbers I've computed. And in order to really stress the point, he jumps from 9 to 120, and he shows how he was able to, on his own, to compute this crazy classification for curves of degree 120. Very complicated, and so giving these examples, that should suffice to demonstrate that the propositions the theorems I have proven, truly solve the general problem of the classification of skew curves of a given degree. So here you see that you have values of n. So for when the degree is 120. N has to be lower than 17 for the classification to be possible. Beyond that, there's no hope. You would need additional characteristics. But that's what's interesting here as well is that you have a table, an example that is used to demonstrate, to faire voir, so to make visible the fact that the method is indeed a full solution of the problem. Right? It's quite interesting. What is the full solution? To a problem that has no solution? It's a procedure, an infinite procedure. And how do you prove that your infinite procedure is indeed valid and general? Well, you give a very complicated example. So you see a lot of non-deductive work going into the treatment of this problem. And obviously the size of the numbers and the sheer size of the table have to demonstrate the power of the method, its application for very high orders, and so on. Okay, so concluding this overview of Halphen's geometrical work here, we have, through these two examples, systems of conics and skew curves. Here's what conclusions we might draw. So first of all, what is the criterion for objectivity here? Well, it's the full and unsayable generality of the theorems that may be asserted about a given object. I must stress here that when Halphen says there is no such thing as a skew curve of degree d or a system of conics of characteristics mu and nu, we're not talking about logical paradoxes. We're not saying that the set theoretic definition of the object would lead to paradoxes or contradictions. In fact, it is very much possible to define those objects. The problem being that if we do so, we cannot say anything general about them. Any general statements about curves, algebraic curves of algebraic skew curves of degree d would fall under certain exceptions, certain particularities with a bit of exceptions. Whereas we are in those more restrained cases, we are able to state general theorems. We are able to state general theorems about plane curves of degree D in the way that we cannot about skew curves. So here the criterion for objectivity is the generality of the theorem that we might express about it, which is perhaps not how we think of objectivity in general. Also, what does solving a problem mean in this context? Well, in the context, because the sort of the natural landscape, the fauna of skew curves is so rich in quirky cases, in monsters, in exceptions, in anomalies. Solving a problem cannot be achieved through a single formula, a compact theorem. Solving a problem means providing a guiding principle for one's navigation of this wild natural landscape, a rational tool through which one may tackle any given problem, any given question, rather than having a one-size-fits-all formula. And I want to stress that in both cases you have this skillful use of analytical instruments, of those extrinsic curves or that have no geometrical meaning whatsoever, whether it's the indicatrice in the case of systems of conics, or those three polynomials in the case of skew curves. You have we have the same skillful use of analytical instruments for the classification of the intelligent complexity of space. We are essentially using these methods to bring back those very complicated objects into the much more ordered and ruly theory of plane curves, of algebraic plane curves, in which we are in possession of a fully mapped out theory of singularities and intersections. So those are ways in which we can describe sort of a naturalist praxis in the case of geometry that cuts across different theories. Skew curves and systems of conics have little to do with one another, but we can point to those structural parallels, those shared approaches towards objectivity and problem solving in the case of Alphen, and which I would argue really echo Golshan's description of Hermite's naturalist mathematics, albeit in a case where, unlike for Hermite, the worry about non-beings is added. There is no equivalent in Hermite's work on quadratic forms, as far as I understand it. There is no such worry about ill-defined objects that lead us astray. So now I want to turn to another geometer, the German geometer Edward Studi, who was in many ways busy with sort of some of the same research questions that Alphen worked on, especially I mentioned Alphen's work on congruences of lines. That's something to which Studi contributed a lot, but also the systems of conics. And so Studi, just to situate him briefly, born in 1862, so slightly younger than Alphen, although not by much, studied under Klein for his habilitation in 1885, back then still in Leipzig, before Klein's move to Göttingen, precisely on the question of systems of conics. And then he went on to visit people like Alphen in Paris, and then had a sort of normal career in German academia. Was a professor in Bonn, mostly, and someone who was very much inspired by the mathematics of Lie and Engel. The latter he met in Leipzig, but who also wrote a lot about kinematics, line geometry, as well as, unlike Alphen or Hermite, a lot of philosophy of mathematics, very polemical philosophy of mathematics, which we'll say very little about today. So his Habilitationsschrift, so his second dissertation that one has to write in order to get a job in German academia, was on systems of conics, on this theorem that Alphen had supposedly refuted, And Studi's point was that, in fact, we can save Charles' formula, that the alpha mu plus beta nu formula that Halfand had supposedly refuted can, in fact, be said to be true. And his argument was, well, what Halfand had in mind in his refutation was a certain conception of what it means for a conic in a system to be a solution to satisfy a certain condition. But in fact, one can raise the question of whether Charles' theorem cannot be interpreted in another way that would make it true generally. And the reason for that is that, unlike Halfand, Studi stressed the fact that the definition of solutions, the way we understand a conic in a system to actually satisfy a condition, that this definition is arbitrary. So obviously so Studi is the same generation as Hilbert, and so you might think, oh well, Studi is one of those formalists. He thinks that mathematics is pure free creation of concepts, the sort of people that Hermit was railing against. But in fact, that is not the case. Studi was very much a realist. If you saw here, one of his last books in 1913 is the realistic worldview on the science of space. And in his unfinished manuscript, Prolegomena to a Philosophy of Mathematics, which is in his Narlas in Bonn, he spends pages upon pages of very polemical writing to rail against the formalists and the people who think that mathematics is purely this human creation, and trying to instead drive home the point that mathematics is a science that bears upon that deals with real objects that have the same ontological robust solidity and permanence as the objects of the world around us. And so here's one particularly interesting quote from this text in his Narlas, where you see how it's possible to maintain at once the freedom of mathematical conceptual work and a realistic worldview. He says, how can the content of mathematics be something objective if the mathematician has the freedom to define as they wish and to conclude in whatever direction they wish? Well, just as the mineralogist who makes a cut through a crystal in order to explore its structure cannot use every cut, the mathematician must also make a selection from his cuts with crystal mathematics. That is to say, conceptualizations. And so the idea being that you have integers, or you have some prime, just like Hermit himself held, you have those prime, you have those natural numbers, which are those sort of ontological atoms, and then mathematics is about building concepts on top of those, and in order to come up with the most fruitful conceptualization possible. And this is something that that is particularly clear in both his work on systems of conics, where he would argue that here that in fact Halfand's refutation is but one way of constructing a concept of solution on top of the solid bedrock that is the conic section. But in fact, there is another way of building such a conceptualization, such a concept of solution that would yield different answers. And so I will not get into that, but essentially that's what he does in his Habilitationsschrift. He explains how you can build a variety of conics and interpret it in a way that saves Charles' formula. But it's also something that he did in the context of line geometry, another topic on which Halfand had written. And this is what I want to say a few words about, because this is quite interesting, I think, to illustrate a different way of building objects, a way that differs not only in the technical tools it relies on, but also in the picture of curve making and object making it is ruled by. So just to give you a brief reminder or piece of information, if you didn't know it already, But so this is building upon this important paper by Julius Plücker in 1864, in which Plücker had come up with ways to study straight lines in space. The idea being that, well, a straight line in space is essentially depending upon four constants, right? So a point in space is defined by three coordinates, but the lines in space have 4 degrees of freedom, so to speak. And Plücker had come up with a way of assigning coordinates to lines in space. So, and therefore, the algebraic treatment of those coordinates yields a way of looking at space not as constituted of points, but as constituted of straight lines. So here's the very brief rundown of how it works. Suppose that you have 2 points in space whose homogeneous coordinates are the xi's and the yi's. So homogeneous coordinates, you need one more than with Cartesian coordinates. And so consider the straight line that passes through both points, and form the cross product xi yk minus xk yi. Those numbers are the line coordinates. So you have 6 such cross products, but in fact, so first of all, they are they define the same straight the same straight line up to scaling, so that leaves only 5 independent coordinates. And in fact, on top of that, you can easily check that you have this this equation that is always true. So that removes another degree of freedom, so you end up with, in fact, 4 degrees of freedom, what you expected. So you have essentially 4 independent coefficients that characterize each straight line in space. And the point being that through the algebraic treatment of those coordinates, and especially for people like Klein and Lee, using certain kind of group theory, you can study projective transformations of space that fix certain points of lines in space. This is something that was very much developed in the early 1870s. Sort of mathematics very much in vogue at the time of Studi's training. And so, in particular, this is quite useful because if you want to look at certain object in space, like certain rule surfaces, you can sort of carry over properties of lines onto those more complicated objects, like surfaces, through such means, and it's something that Klein did. But Studi turned to this theory whilst being interested in another kind of complicated geometrical phenomenon, which might be described through lines, namely kinematics. He was interested in rotations of bodies, couples and moments after Poinsot, those kinds of theories. And he found out that this formalization of what lines in space are did not fully capture the features he wanted to focus on. That this was a way of turning lines in space into a mathematical object of its own that did not really achieve the goals he had in mind. And so in a very important paper in 1903, as well as in his book on the matter, he wished to argue that there was another way of turning straight line in space into a mathematical object susceptible of such treatments that would better suit his purposes. So I will skip these quotes. I will skip all that, but well, I mean, I can share them to you if you want to know about. So essentially he wrote a sort of a genesis of this account. He said, well, when we want to turn a geometrical object such as a straight line in space into something that we can discuss, that's something that we can study, we have to turn it into what he calls a contorted manifold, a closed continuum, abgeschlossenes Kontinuum nach Kantors Definition. And so the problem being that if you want to say anything about the lines in space, you run into exceptions, into problems. So for instance, you can't say, or just even think of straight line in plane, you can't say that two straight lines always intersect because you can have two parallel lines. So you add a point at infinity to be able to say that straight lines always intersect. And similarly, adding the point at infinity is a way of turning the straight line into what he calls a closed continuum. And that's a price to pay. You start with your actual straight lines, you add artificial concepts, you carry out this operation which he calls Begriffsbildung, so you conceptualize on top of what is real in order to achieve the construction of an object that you can actually say general things about. And in the same way, he says, well, what Pluquet had achieved is adding infinite lines at infinity, lines in infinite plane, so as to be able to say general things about lines in space. But, and so this is particularly useful because it allows you to generalize projective geometry in space. It allows you to give theorems analogous to things like Poncelet's theorem or Briancham's theorem in space in a general manner. It yields a continuous group of transformations, has lots of good qualities that you may want to do a certain kind of projective geometry in space. But he goes on to say, though such concepts are creations of our own, they are creations that they are things that have purposes. They are creations for a goal, for a purpose, and that we should not dogmatically accept and keep them. We should always check how much they are fit for our purposes. And in his book on dynamics, he goes on to create different ways of turning those straight lines into a closed manifold. So this, I won't get into the details, but essentially he provides us with another way of adding lines at infinity that preserves not projective properties, but properties related to orthogonality, properties that have a certain meaning for the purpose of doing kinematics. We can discuss that at another point. So essentially, he had points rather than lines at infinity, and anyway. And so he ends up with a different group of transformation, a different equation, that has impact on the validity of certain theorems that were true in Pluquet's line geometry become false and vice versa. But his point being that he has achieved a concept of line continuum that is more suitable for the study of certain kinds of properties. And so, just to give you an idea, so what does mathematical practice look like in this book? So this is his book on dynamics. The first section is the following. The first section is a non-formalized description of geometrical motions and rotations and things like that. And he's looking at things like what happens when I have a sphere that rotates, and I look at what happens to my vectors on my sphere, and I observe really very much certain properties, like the fact that rotating in one way and another is commutative whereas insofar as my vectors are concerned. So he's looking at, you see, for instance, the geometrical additions of motions, of rotations, the commutativity of certain operations on vectors on a sphere or things like that. And this is very much done so you have symbols, but you have no complicated algebraic framework. This is very much done with a very simple symbolic apparatus. And in the second section of the book, as well as the third, then you introduce coordinates and parameterizations. And he explains here, he says, well, the research that we carried out in the first section must now be turned into a system of analytical geometry. And what does that entail? Is the creation of specific signed citation through which we can restore the formal simplicity and of the properties observed in the first section. And here, and this is where and in this context only does he introduce such groups of transformations, such parametrizations, the sort of the analogous systems of coordinates to clickers. So you have this, another kind of almost empiricist practice of mathematics, where you begin with a very pre-formal description of your geometrical properties, and then in the second time you come up with the proper formalization for it, and obviously drawing inspiration from pre-existing formalization, but still. So you see that in terms of justification and the justification arises at least partly not just from internal coherence and algebraic rigor, but also from observation and engagement with pre-formal properties. So how can we describe Schulli's mathematics as another kind of naturalist mathematics? Well, here, unlike with Halphen, we have an emphasis on the free creation of concepts atop the bedrock afforded by real objects, real being both, in Schulli's text, eigentlich, so actual objects, and real as not complex. We begin by looking at real straight lines, that is to say, straight lines defined by finite real coefficients. And then we construct. And then we need to add points at infinity, imaginary coefficients, and so on, so as to make it into the sort of mathematical concept that yields general theorems. So here we have a practice of mathematics that tries to bridge the gap between the creative nature of the endeavor and the realistic outlook on what is being described, what is being studied, what is being discoursed upon. Another feature of this mathematical practice is the goal-oriented use of symbols. Symbols, in Schulli's case, are introduced after a first exploratory engagement with a specific object. So in this case, rotations, couples, and so on. And Schulli stresses the tailoring of those symbols for a specific object, for a specific problem. So rather than having this theory of analytical curves and singularities that is this master tool for analytical descriptions, here we have symbols that are something to be created in reaction to a first exploratory survey of geometrical space. Although Schulli shares with Halphen worries about the lack of rigor and precision in modern geometry, the epistemic virtues through which he thinks we can remedy this situation are not the same. We don't have the same observation, attentiveness, patient classification that yields those massive tables, but rather we have the promotion of an attitude by which the mathematician has to be discerning. He has to select properties that they wish to preserve and build into the formalism. So values like creativity, selectivity, independence, autonomy are perhaps more important than observation, patience, tolerance towards the many quirks of nature. So a different portrait of mathematician as an epistemic actor. And here we have a mathematical practice in which mathematical order is really available. It is not natural; it is conceptual creation, but it's something that you can always hope for, that you can strive for, that you can make come about, provided that we are sufficiently skilled in our theorization. So very much a different way of making geometrical nature come to life. Okay, and so, oh, sorry, this is a problem with the justified. So what I want to stress here is that although I've been very fast and vague with my description of those texts, which are very complicated, I think those descriptions do not rest upon programmatic statements, which we can find in Halfen's letters or Studi's philosophical writing, but really speak to the practice themselves, the use of and construction of notations, the formation of specific kinds of results, whether we think that classification itself is a result or that conceptualization is a result, both non-deductive endeavors that nonetheless are important pursuits here. We can describe at the level of mathematical practice itself the adoption and pursuit of certain epistemic virtues and attitudes, and so on. I think another uptake of such outlooks is that we can describe a very local case study, like Studi's and Halfen's disagreement over systems of conics, yet do so in a way that yields broader perspectives on what is at stake beyond simply the disagreements about the truth of a theorem or the difference in concepts that they use. We can use this case study and through that perspective make it speak to broader questions. And so, if you are familiar with Jamal Arena and François Hallé's recent challenge to move beyond localism and case studies, I think is perhaps a useful perspective. And lastly, I think there's perhaps here material to provide a new picture of the so-called modernist transformation of mathematics, an episode in which notions of objectivity and contrasted pictures of objectivity have always been made to be very important. And so I think here describing objectivity very much at the level of practices in these senses, in these ways, can be quite fruitful. So I hope this is a way to look ahead, and thank you for your time.